Hello and welcome to O Morgan Labs. Today we're going to find the speed of this block here at the equilibrium position. We're going to use the conservation of energy. Basically, the kinetic energy of the block is going to be transferred into the potential energy of the spring. Conservation of energy. So no energy is lost or gained. It's just transformed from kinetic to potential. And then we're going to use the spring force, F equals kx, and then the gravity force or weight equation, m times g. Okay, it's going to be at equilibrium when the spring force equals the force of gravity. So you set the equations up, kx equals mg. We know k is 200, so it's 200 times x. We know m is 2 kilograms. We know g is 9.81 meters per second squared. We work that all out and do the algebra. Solve for x equals 0.0981. Next, we find the potential energy of the spring at x equals 0.0981. Then we subtract that potential energy that we're saying is being transformed from the kinetic energy at 0.45 meters. To make things a little bit less complicated, we're going to round to the nearest tenth as far as the displacement at the beginning. So 0.0981, we're just going to say 0.1. So the potential energy of a spring at 0.1 would be 1/2 kx squared, where x is 0.1. We plug in the numbers and we get 1 joule. So at the equilibrium position, the spring is going to have absorbed 1 joule of energy from the block. Okay, so the next thing, we have to find the kinetic energy of the block. Now you could do a dynamic analysis, the one-dimensional motion with acceleration, but it's easier than that. You just realize that since you're falling in a gravity situation, you just use mgh, which is basically your change in your potential energy, and that's going to equal your kinetic energy. So we're using the conservation of energy due to gravity, right? We're kind of using that little principle, so we don't have to use the one-dimensional acceleration, all those equations. After we do that, we say, okay, mgh, m is 2, g is 9.81, h is 0.5. We get 8.829 joules. That's the change in your potential energy, which equals your kinetic energy. Conservation of energy. That's why we can do this. Now remember, we want the speed at the equilibrium position, so it would have absorbed 1 joule of the kinetic energy as potential energy. So we minus 1 joule absorbed by the spring. So the remaining kinetic energy of the block at the equilibrium position would just be this 8.829 joules minus 1 joule, which is 7.829. So that's the kinetic energy of the block when it hits the equilibrium position. So the last step, we back out the velocity from 7.829. So we know the kinetic energy equation is 1/2 mv squared. And we know kinetic energy is 7.829. So all we do, plug in, we know mass is 2 kilograms. So we plug in everything, 7.829 equals v squared. Take the square root of that, and we get velocity is 2.798 meters per second. So there you go. There you have it. The speed at the equilibrium point is 2.798 meters per second. So you would need this if you're trying to calculate, the strength of a spring or something, right? You're trying to maybe size a spring, and you need the spring to maybe catch some type of projectile or something. This would be a good hand calc you could do to kind of size your spring. But you would use different variables as the unknown. The speed wouldn't be the unknown. The speed would be like your 2, I guess, 2 meters per second. and then you would know your mass, and then you would kind of calculate the spring constant, and then figure out what spring you need. Or it could have any other uses. So just keep this in mind. This is just practicing your going from kinetic to potential. Okay, hope you learned something. Uh, like and subscribe. Thanks.